Figure 660 has some interesting notations. First of all, we're looking at a tolerance 750 to 745. So when we have a limit distance, that means that there is a mating slot in the assembly that has to fit into, and we're going to calculate clearances. And so we'll expand on that conversation a little later. We have a counter bore for a clearance for a bolt or a socketed cap screw. Since the depth is only 350, that seems maybe a little light and not quite big enough for a ½ inch, so we'd want to check that geometry, figure out which screw we're going to use or bolt nut combination that to attach that. And then the heat treat 10-250, kind of looked around to see what that notation works, but because we want increased wear resistance, it's probably going to be some kind of surface hardening, meaning it's not going to be hard all the way through, but anywhere from 10 to 20 thousandths deep is going to have a pretty good hardness rating so that it won't wear out. Alright, so other than that, our geometry, kind of like the front profile, and then we can either build up if we did just this first T portion, or we could go ahead and build it out and then remove material as we go. So probably just looking at this, go with the kind of T shape, and then we'll add some geometry to it. And then I think I would like the origin to be at the bottom middle again. So new part, we're in inches, so that's already set for our units. Do the sketch. We have 1 inch on one side. Well, that's to the groove. So 1 1/4, 1 1/4 be 2 1/2, and 0.75 would take us up to 3.25. So we have symmetry in the part. So vertical, infinite length, and then we'll select our geometry. So that gives me enough to get started with, the right to left selection and mirroring the entities. Well, we're going to save that limit dimension for a little while. The height is 0.62. The width we said was 3.25. And the outside leg was 1.25. And then the step of 0.19, and then based on the tight tolerance, that one's still pretty well open. We can recognize that as being close to 0.1875 or 3/16, 0.62 being real close to 0.625 or 5/8. Alright, so we get that fully defined, and then if I go to measure this, it's coming out at 750. And so if I make that my geometry, then I'm going to get that over defining condition. Do I want to leave that item driven? Well, since there's a limit dimension on it, it's kind of the more critical of the two. So this would be one that I would be interested in coming over to other, reassigning its the parameter to driven, and then I can come over to the 0.75 and reassign it as the driving. Right. And then when we look at the tolerance and precision, now I can set the limit dimension, and we're going to have a -5 thousandths on our number. But within our tolerance zone, plus or minus 10 thousandths, 5 thousandths doesn't register. So I need to, oh there it is, find the document precision and switch it over to 3 decimal place so that we actually have something that's usable. Alright, so this starts the conversation on maximum material condition. For this outside geometry, the most material will be the 750, which is what we ended up with. If I were to draw this sketch at 0.745, then the issue would become that if we CNC machine this, I'm going to use this geometry or use a sketch from this geometry, it's at the low end of the tolerance, and the tool and any other compensation that the machine tool would need is already at the minimum, threatening to scrap the part. Right, so I want to be able to control it and hit that mid-range. The other thing is we need to look at the stack up in the clearances, which is a pretty involved discussion on how we would decide what's the minimum allowance, any kind of interference if this was going to be a press, and then what the tolerance on the other side to have a maximum, have the maximum clearance allowable for the part. So on the slot, kind of our first pass would be 750 to 755 on its internal geometry, but that means if this part's made at 750 and that part's made at 750, they are going to be at a transition fit. They probably will not go together. All right, so give you a little preview of discussion coming up. All right, so 250 on the width. I'm going to open up a sketch on the top. Probably don't need to convert geometry, but just to review, if I control select the three edges, let go of the control button, the convert entities they show as attached, but they really are not coincident with the endpoints of the line, so I can pull those back, and we're going to have a width of 0.25 and an angle of 40 degrees. Make sure I get that internal. As I drag around, I'm going to get those alternate solutions. See that I missed a line in here. Okay, so that one is 1 inch 250 from the back side. Okay, so really with the contours and regions I wouldn't have to trim that out, but certainly not going to hurt. So trim to closest is my preference. Power trim means you're going to left click, drag, and whatever it crosses goes away. Corner, trim away inside, trim away outside. I think my comment is that I don't trim regularly. Most of the time I'm going to use those contours and regions or have that available for something else. But in this case, we'll clean this up a little bit and make that go away. And then when I go to extrude this out, rotates over, and we have some math to do. Or, since I really wouldn't want to put this on the bottom of the part, this is a really good place to use the offset from surface. So when I pick that bottom geometry, we have a total height of 1.56. The 0.56 is real close to the 0.5625, which would be 9/16. And then I need to reverse some geometries so that I'm going to try the reverse direction first before I reverse the offset. So the offset would change it in relation to the face, where the direction just reverses. Okay, so the hole location, let's go ahead, and one of the things that I do to use the S key, and it's one of those habits I just haven't adopted, but S key is another option. We'll quickly look at the donut. If you right click, hold down, you will see the donut, and that will come up with the views. And hit Control 7 to get back to the top. Got ahead of myself and hit the sketch, so I'm just going to discard. S key, and in the bottom right is going to be the hole wizard, and we're going to see what we can find close for a binding head screw, a heavy hex bolt, a hex bolt, a hex finish bolt. And really the issue with any of the hex bolts is we need enough clearance to get a socket or get a wrench in, so more likely a socket. Or for a socketed cap screw, we would need enough depth so that the top of the cap screw is not sticking up above the part. So I'm going to assume that this is binding, philoster, or hex based on the call out, and we'll go ahead and see what we get in the way of geometry when we're setting the parameters. So we have clearance if we go with a normal fit and show the custom sizing. And so it's a 30-second over, which I believe would be 17/32, and that one does not match. So 500 through, maybe that would be a 7/16. So the through hole at 1/2 inch. How about if we go up to loose? Alright, so 484 with a 1 inch for the clearance. Yeah, not sure what that call out is doing. 316 on the depth. So if I know that this is a 7/16, and even with the loose fitting, go back to normal, it's staying at 1 inch. I have a tendency to believe that, but I also want to think it's going to run into the edge, which whatever we put in there, if we can't tighten it, it's not going to do us a whole lot of good. So on the off chance that it is, let's just go through, look at the binding head screw, and I think for a clearance about 3/8 is the largest we can go there. We'll go ahead and see what we get. Through 812, 253, and then the philoster. And these I'd have to look up. I don't remember these right off the top of my head. 453, 650. Alright, so we're not finding anything super close. So I'm going to make the assumption that it's a hex bolt, and we're going to override. And I just want to be careful with these because they are usually pretty close. I start making a lot of adjustments. I want to consider the legacy, but when this goes into the assembly and we've actually putting this together, doing whatever we need to for our geometry, then we'll place the bolt, make our picks, and see how it works out. Alright, so on center line we have the inference line, and then our dimension 0.75 from the front. Alright, so there's no dimension for the horizontal, and I picked the wrong one, so Control Z, I'll come over and do vertical, and we'll go ahead and accept. Alright, so the question then would be, based on the size of the hex bolt, we have enough room in there. I almost want to err on the side of caution and go ahead and put in that extra diameter. Okay, so the other angle for the relief on the corner, we'll just draw the rectangle. This could have been an open profile. We have 50 degrees on the lower side and a width of 1 inch. And then this is going to be 190 deep. And again, if you recognize these numbers, see that that would be close to 3/16, 1.87, 1.88, depending on how you're rounding, or 0.1875 if you take it out to the 4th decimal. Alright, so on the angle, let's go ahead and treat this as a chamfer. And we'll want to set to the 30 degrees and 0.94. And I do know that that would probably be, what, 15/16, 0.9375 if we look it up in the chart. Alright, so the angle doesn't look too good that way, so if we flip the direction, I think that's going to get it. If it was still off, still a little bit weird, we could come back and change to the adjacent angle of 60 degrees, see what we get there, but I think that's going to be our solution. Alright, so let's apply the cold rolled steel. And then we'll save this, and we're ready to move on into some drawings.